Dear students, in the previous lecture, I have explained you the first law of thermodynamics, which is the law of conservation of energy. It relates the heat absorbed and the work performed by the system or on the system. But it does not give any idea about the direction of the flow of heat, although heat flows from the body at the higher temperature to the body at a colder or the lesser temperature. The naturally occurring processes, whether physical or chemical, have the tendency to go in one direction. For going in the reverse direction, they need external agency. For example, water fall down the hill. It comes naturally downwards, but water cannot flow up without any external agency. Similar examples we will see in the coming slides, and we will understand that what is spontaneity and what are the spontaneous processes. Spontaneous physical and chemical processes. A waterfall runs downhill. A lump of sugar dissolves in a cup of coffee. At 1 atmosphere, water freezes below 0 degrees Celsius and ice melts above 0 degrees Celsius. Heat flows from a hotter object to a colder object, or when the iron is exposed to oxygen and water, forms rust. All these processes are spontaneous. They have the tendency to take place of their own, and the reverse of all these processes need an external agency. Spontaneous process, a reaction that will occur without outside intervention, but we cannot determine how fast. Flow of a water down a hill, it is a spontaneous process, but the reverse needs an external agency. It takes place by themselves. For example, if we put sugar in a glass of water, it automatically dissolves, but the reverse we cannot expect, that is, the dissolved sugar forming a lump. In the figure we can see that there is a gas in the one chamber and there is a partition and the other chamber is evacuated. When we remove the partition, the gas diffuses from one chamber to the other chamber automatically, very naturally and by itself. But the reverse process is not take place of its own. The reverse process is non-spontaneous. The spontaneous processes are those that can proceed without any outside intervention. We can see in the figure that the gas in the vessel B will spontaneously effuse into vessel A, but once the gas is in both the vessels, it will not spontaneously separate. There are many spontaneous processes which takes place after proper initiation. For example, if you lit a candle, it burns until it is all over. Heating of the calcium carbonate. When we heat calcium carbonate, give it the required conditions, it gives calcium oxide and carbon dioxide. So, some reactions are spontaneous, some processes are spontaneous after proper initiation or proper start. Rusting. Rusting is also a spontaneous process. When an iron object comes in contact with the moisture and air, it rusts, but the reverse process is not possible. Processes that are spontaneous at one temperature may be non-spontaneous at other temperatures. For example, above 0 degrees Celsius, it is spontaneous for ice to melt, and below 0 degrees Celsius, the reverse process is spontaneous. So, now we can see the many characteristics about the spontaneous processes, and these are: under some given condition, they may take place by itself or by initiation. They can take place by itself or has an urge or tendency to take place. They are independent of rate, and the rate may vary from extremely slow to extremely fast. Now, what are the reasons behind spontaneity? why are some processes are spontaneous, why they have the urge to take place of their own, what are the driving force behind a process to be spontaneous. Now again we will study this through some examples. Tendency for minimum energy. In order to acquire maximum stability, every system has tendency to come in the state of minimum energy. Minimum energy, maximum stability. For example, water comes down the hill because its potential energy decreases. Heat flows from the hot body to the cold body, again there is a decrease in energy. These both are the spontaneous processes. All the processes are spontaneous because they have tendency to acquire minimum energy. Delta H is negative. From this graph also we can see that the enthalpy of the reactants is higher than the enthalpy of the products, and the difference of the energy is evolved as heat. The process is exothermic. Limitations for the criteria for minimum energy. But there are many naturally occurring processes which are endothermic, but they are spontaneous. For example, melting of ice or evaporation of water. These are endothermic processes, but they are spontaneous. By these examples, we can say that the decrease in the energy or the decrease in the enthalpy cannot be the alone criteria for the process to be spontaneous. Here are the examples of the reactions which are spontaneous, but 2 of them are exothermic and 2 of them are endothermic. Like combustion of methane into carbon dioxide and water, it is an exothermic process and it is spontaneous. The hydrogen ion and hydroxide ion are combining to form the water. Again it is exothermic and spontaneous. But conversion of water solid, that is ice, into water liquid is spontaneous, but it is endothermic. So the heat or the heat content or the enthalpy, it is not only the criteria for the process to be spontaneous. Hence, there must be some another driving force which together with the enthalpy is making the process spontaneous. The another driving force is randomness or messiness, or you can say that disorderness, and this is an important thermodynamic function or the parameter known as entropy. From the figure now you can see that a solid which is very much ordered is changing into liquid, and when the solid substance is changing into liquid, there is disorderness, and when the liquid is changing into vapor state, again there is more disorderness. In the third figure you can see that there is a solvent and solute. When they intermix to form a solution, there is high disorderness. All these processes which are involving increase in the disorderness are spontaneous. Let's see some more examples of entropy. In the figure you can see that there is a glass full of ice chips and the other glass is full of water. Just on the physical looking, we can say that the glass in which ice is there is more disordered as compared to a glass in which liquid water is there. But actually it is not the case. In which there is ice chips, physically seems to be more disordered, but the ice is the solid state of water, and in the solid state the water molecules are more ordered arranged as compared to the liquid water. So the ice is, in ice there is less disorderness as compared to the liquid water. Here again the entropy, that is randomness. From the figure we can say that the A state is more ordered as compared to the B state. B is more random. In nature, where do you move? From disorderness to orderness or orderness to disorderness? The natural tendency is to move from ordered state to disordered state. Even in the class, students, when the teacher is not there, you enjoy the disorderness. The entropy is very high when the teacher is not there in the class. But as soon as the teacher enters the class, there is orderness, there is decrease in the entropy. Second law of thermodynamics. If the two objects are not at the same temperature, then heat will always flow from high to low temperature. Hot object will decrease in temperature and the cold object will increase in temperature until they are both at the same temperature. The entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. The entropy change of the universe should be greater than 0 for a process to be spontaneous. And for an equilibrium process, the entropy change of the universe should be equals to 0. Entropy can be thought of as a measure of the randomness of a system. It is related to the various modes of motion in the molecules. The mathematical expression for entropy is represented by the capital letter S. It is a state function, that is, it depends upon the initial and the final state of the system and not on the path. It is also an extensive property. It depends upon the amount of the matter. Mathematically, entropy is equals to Q reversible upon T, where Q is the heat absorbed by the system. When a system absorbs heat, the motion of the molecule increases and hence the randomness also increases. But it also matters that at what temperature the heat is absorbed. When the temperature is low at which the heat is absorbed, then randomness is more, and when the temperature is high at which heat is absorbed, then randomness or entropy is less. From the figure you can see that entropy is a state function. It is a mountain and there are two hikers and they are starting from the same point and they are again reaching at the same point, but both have adopted the different paths. But the distance between the starting point and the end point is same, whether the path is followed the same or different. Similarly, entropy is also a state function. It depends only on the initial and the final state and not on the path. Just like enthalpy change and internal energy change, we calculate entropy change. Entropy change, that is delta S, is equals to entropy of the final state minus entropy of the initial state. Today we studied about the spontaneous processes, the processes which have tendency to take place of their own, and about the entropy, that is randomness. And we also studied about the two driving force to make a process spontaneous. We also studied that alone enthalpy change or entropy change cannot be the deciding factor for a process to be spontaneous. In the next lecture, we will study about another thermodynamic function, Gibbs energy, which will correlate enthalpy and entropy, and then it will decide the process to be spontaneous or non-spontaneous. Thank you.